Hello students, today we are going to see the one more application of the differential equation. Okay, now let us solve the problem. The problem is like that a body of mass m falls from rest under gravity in a fluid whose resistance to motion at any instant is mk times its velocity, where k is constant. Find the terminal velocity of the body and also the time taken to acquire one half of its limiting speed. Okay, now consider this problem. In this problem, we are given a body, that is, here we are given a body of mass m falls from the rest. Falls from the rest means it is at the rest position under the gravity in a fluid. It is fall in a fluid whose resistance to motion at any instant is the m into k times of its velocity. Now let us consider here this is a beaker, or this is a beaker and this is a fluid in this beaker. Okay, here that body is falls from rest position to the uh, some motion. Okay, initially the body is at a rest position. It falls under the fluid. The fluid is having some acceleration due to gravity, that is g, small g, and some velocity also, and that body having the mass m also. Okay, now let us consider, let v be the velocity of the body at any time t. Okay, at any time t, the v is the velocity. Then the equation of the motion of the body is given by, according to the Newton's second law of motion, we will get mass multiplied by acceleration is equal to weight of the body minus fluid resistance force of the or the resistance force of that fluid. Okay, when the body is at the rest position, when these both forces are equal or balancing to each other. Okay, it is given in our problem. Then again consider mass into acceleration is equal to weight of the body minus fluid resistance, that is the resistance force which is applied by the fluid. Okay, the mass is given by the m. Acceleration, we know that the rate of change of velocity with respect to time, dv by dt, which is equal to, again, mass is the body mass, and g is the acceleration due to gravity, minus m, again mass of that body, k is the constant, and v is again the velocity. Okay, now the equation of the motion is m into dv by dt is equal to mg minus mkv, taking m common from each side and it get cancelled here. Okay, therefore after that we will get dv by dt is equal to g minus kv. Therefore dv by dt is equal to g minus kv. This is the equation 1. Now separating the variable. Separating variable, we will get dt is equal to dv upon g minus kv. Now next step is the integrating. Integration of dt is equal to integration of dv upon g minus kv. Therefore t is equal to minus 1 upon k log of g minus kv plus c. Okay, integration of 1 upon any function is the log of that function multiplied by the multiply with the coefficient of the coefficient, means 1 upon k. Therefore since body is falling from the rest, means initially its velocity is also 0 when time is equal to 0. Okay, body at the starting point or at the start, the body is falling from the rest position. After taking the rest position, the body start falling. Okay, we have at the rest position, we have velocity is also 0 and time is also 0, t is equal to 0. That body is constant or ideal at that place. Therefore by substituting value, we will get 0 is equal to minus 1 upon k log of g minus 0 plus c. Therefore value of constant c is equal to 1 upon k into log of g. Now substituting the c in equation 2, we will get here t is equal to minus 1 upon k log of g minus kv plus 1 upon k into log of g. Okay, here we are simply taken the doing some adjustment here, or we will say the simplify. T is equal to this plus 1 upon k log of g I had taken first time, and at second minus 1 upon k log of g minus kv. Again I had take 1 upon k common from both the functions. Therefore t is equal to 1 upon k log of g minus log of g minus kv. Here again the subtraction of logarithmic is there. Therefore that means that functions must be divided. Okay, therefore t is equal to 1 upon k log of g upon g minus kv, which is equal to 1 upon k log of now separating the denominator, we will get g upon g minus g upon kv. This is equation number 3, or we will simply simplify t is equal to 1 upon k log of 1 minus g upon kv. This is the equation number 3. After simplifying I had get this term. Okay, we know that the terminal velocity is attained when the terminal velocity we will attain or achieve when the weight of the body is exactly balances the resistance to motion. Okay, weight of body is equal to the resistance of that motion. If v is the terminal velocity obtained by the body, then if v is the terminal velocity, okay, then mg is equal to mkv. Now m get cancelled, therefore g is equal to kv. Therefore the k is equal to g upon v, or v is equal to g upon k. Now substitute this v is equal to g upon k in equation 3. We will get t is equal to minus v upon g log of 1 minus small v upon capital V. This is equation number 5. Okay. Now let us consider when at time t is equal to t1. Okay, we have to prove that at time t equal to t1, when small v is equal to 1 by 2 of capital V. Then the equation number 5, we have this is the equation of the motion we will get here. Now we are substituting the given conditions that we have to prove, that at time t equal to t1 the velocity v become the 1 upon 2 capital V. Okay, then equation number 5 becomes t1 is equal to minus capital V upon g into log of 1 minus 1 by 2 v upon capital V. Okay, in throughout this equation capital V we are using, and we are replacing the small v is equal to half of the velocity, that is the capital V. Therefore t1 is equal to minus v upon g log of 1 by 2. Okay, here minus sign is there and 1 by 2 is there, therefore 1 by 2 becomes the 2 here and minus sign get cancelled. Therefore t1 is equal to v upon g log of 2. Hence we can conclude that the body attains the 1/2 of its limiting speed, whatever may be the speed at the initial point, then it attains the half of that speed at time v upon g. At time we had calculated here time v upon g log of 2, the terminal velocity of a body. Okay, here the final time taken is the v upon g log of 2 seconds, and v is the terminal velocity of that body. Hence we have proved here. Now we are here introducing the new term that is the terminal velocity. Terminal velocity is the when resistance become equal to the weight, the acceleration becomes 0. Okay, when the resistance applied by that fluid, resistance or the force of resistance applied by the fluid becomes equal to the weight, then acceleration become 0 and the particle continues to fall with a constant velocity, because rate of change of velocity becomes the 0, therefore acceleration becomes 0. This is called as the limiting or the terminal velocity. Okay, therefore hence we had proved that a body attains the one half of its limiting speed at time v upon g log of 2 second, where capital V is the terminal velocity of the body. Thank you students. If you have any problem, then please write me in the comment section box. And if you like my channel, please subscribe it, like it and share it. Thank you students.